All right. So there should be floating around the participation questions. I apologize I got here a little late. So most people are already in the class before. And so if you didn't get them, I don't know where extra floating around. But anyone not getting any that's here? No. All right. Thanks for passing those around. All right, so today we're going to be finishing up chapter 14. Okay. We will then have an exam on chapter 12, 13, and 14 starting Wednesday as well as on Monday. Okay. So any questions that people have about anything before we begin today? All right, then. If there are no questions, let's get going. So first thing we'll start kind of talking about today is finishing up just one last little bit before we get to kind of reaction mechanisms and catalysts and things of that nature, is talking about half-life for a chemical reaction. Okay. Right, we talked about integrated rate laws, and those integrated rate laws gives us the dependence of the concentration on temperature, right? How does our concentration change with some change in temperature? Okay. And related to that is this idea of half-life. Anyone have any know what the half-life is defined as for a material? Yeah, right. It's basically given by its name, right? Half-life is the time it takes to get to half of the concentration that you are currently at, right? So if I have 10 moles, right, how long does it take to get 5 moles of this after the reaction's gone, right? Right, if I have 5 moles, how long does it take to get to 2.5 moles, right? Just as long as it takes to get to 1/2 of its initial concentration, right? That is what the definition of a half-life is for a material, right? For a first-order reaction, okay, so this equation here is only true for first-order reaction. So for a first-order reaction, the half-life is inversely related with the rate constant K. See here, ln of 2 is just the number, 0.693, and it's 1/K. Okay? So for a first-order reaction, the half-life is inversely related with the rate constant, right? Which should make sense, right? The faster your reaction is, right, the rate constant is related with the speed of the reaction, right? So the faster your reaction, the larger the rate constant, the less time it takes to get to half the initial concentration, right? So conceptually, that should make sense that these things are inversely related with each other. Okay? Actually, I forgot to address this question on Zoom, right? Will there be participation questions on exam days? No, for those who are in class taking exam, there won't be. And for those online, I'll just have participation questions for essentially the next 2 weeks, if you will, right? So people on Monday will have participation questions today. but not next week on Monday. People on Wednesday will have participation questions Wednesday next week, but not on Wednesday this week, because you'll be taking the exam. Okay. All right, and then for those online, for these 2 weeks, you'll just have one set of questions that'll post sometime to do. Okay. Yep.
So you have to appear in Zoom on Wednesday or no?
No. So yeah. So if you're not taking the exam on Wednesday, you do not need to be here on Zoom or in person, right? Because I'll be using the exam Zoom meeting thing. I have a couple different settings on there than what I have on the regular class Zoom link. So I won't even use the regular class Zoom link, things like that. There won't be anything advertised on there yet. So for those who are here in person today, you don't need to do anything Wednesday, got the day off, at least from this class, right? For those who are taking an exam on this Wednesday, next Monday, you don't have anything you need to be doing. Take the day off, right, from this class, okay? Any other questions? All right, so, right, as saying, right, again, the half-life for a first order reaction is inversely related to its rate constant. This relationship between half-life and rate constant is true for any order. They're inversely related, but specifically the equation here is only true for first order. And the unique thing about a first order reaction is that its half-life is independent of the concentration, right? That you see here the half-life, right? Pointing at my screen, right? This half-life here, right, does not depend on what is my initial concentration. So the time it takes for 10 moles to decay versus 1 mole versus 0.05 moles to decay is the same from half of its initial concentration, right? So the time it takes to get to half of its initial concentration does not matter on what its initial concentration is. Now, for second order reactions, that's not the case. Second order reactions, the half-life depends on the initial concentration. It's directly proportional. I forget the exact equation, but it's something like T1/2 is concentration initial over K, something roughly like that. It's in your textbook. I'm gonna look up the exact equation, right? But for second order, the more stuff you have, the faster it decays. Okay, and so for second order, the half-life will depend on what the initial concentration is. Okay, and yeah, and so on and so forth. Third order, fourth order would be the same thing. So it's only first order that's independent of your initial concentration. Okay, this is what makes. So we'll talk a lot more about this in chapter 20 when we talk about nuclear chemistry. Okay, that's what makes a lot of reactions in nuclear chemistry very unique, and why we can do things like carbon dating and other things like that, because of the fact that the half-life is independent of whatever the concentration is of our material. Okay, just sort of a fundamental property of that reaction. Okay. All right. So for a, I guess they don't specifically state here, but let's consider only a first order. Oh, actually, no, this is not asking time. So no. This works for any of them, right? So after 3 half-lives, what percentage of the initial reactant remains? Okay. It's going to be 6.25%, 12.5, 25, or 50. After 3 half-lives have occurred. Some people saying C, some people saying get rid of B. Right, so 3 half-lives, right? So let's just count them out, right? 1 half-life goes from 100% to 50%, right? Definition of half-life, you reduce the concentration by half. Another half-life takes that 50% and brings it down to 25%. And then the third half-life brings that 25% down to 12.5%. So B here is going to be the answer. After 3 half-lives, I have 12.5% of my initial concentration. Okay. All right. Okay. Any questions related with half-life? Okay, so Jordan, can you explain that again? Yeah. Right. So I start off with 100% of my initial concentration, right? After one half-life, I reach this 50% of my initial concentration. Then after another half-life, I'll get to 25%, right? Because I reduced my 50% by half to get to 25%. Then after one more half-life, I take my 25% and it gets reduced by 1/2, and that gives me 12.5%. Okay. So each half-life, you're multiplying your concentration by 1/2, right? So you multiply your initial concentration of 100% by a half, by half, and by half. And that will give you 12.5%. Any other questions about half-life definition? All right. So now let's start talking about reaction mechanisms. What is a reaction mechanism? How would you describe a reaction mechanism? Is every chemical reaction just, like, let's say if I wrote out the reaction of H2 plus, or let's see here, 2 plus H3H2 going to Na2NH3, right? Let's say I write this reaction out. Is this a reaction mechanism? No. Why not? Yeah, so reaction mechanism typically has multiple reactions. Not every time does it have to, but typically a reaction mechanism involves multiple reactions that do what? What do those multiple reactions do? Take you from where to where? Yeah. So yeah. What I'm getting at is kind of what you're saying there, right? Where it. Let me put this back up, right? So for this, right. So it involves multiple steps that take you from reactants to products, right? So the reaction mechanism for this chemical reaction, right? The reaction mechanism for that chemical reaction would involve multiple steps, potentially that takes you from the reactant to the products. And what is unique about those steps? What kind of reactions are those called? What kind of steps are those called? Something that we're going to have to then define again in just 1 minute. So some type of step. Elementary step, right? Written right there on the slide, right? Involves multiple elementary steps, right? That take you from a reactant, from reactants to products, right? Okay. Right. The sum, and then the sum of those three steps gives you the overall reaction. So another way of, and then so the sum. So if you add up all those elementary steps, right, you get the overall reaction, right? You go from reactants to products, right? Sort of the same with two different ways of saying the same thing, almost, but right. And so, what is an elementary step? Or an elementary reaction? Right, so an elementary step elementary reaction, right? So single step in a mechanism, that's true, it is a single step. What's different between, right? So I just removed again that reaction, right? N2 plus 3H2 going to NH3, right? That reaction, what's the difference between that and what one would have as an elementary step in the reaction? Yeah, so intermediates. So yeah, so they can use that. That's true. Let's see here. I'm looking for something. Right, elementary step and elementary reaction. I just can't find a better way to try to ask the questions like that. Right. These, like, right, an elementary step or elementary reaction, right, describes how things are actually reacting, right? What things are hitting together, what things are combining, right? Our reaction, right, that like reaction N2 plus H2, I don't know why I keep on deleting it, right? N2 plus 3H2 and then 2NH3. Right, this reaction here, okay, is just some general chemical reaction. Well, this reaction does not occur by having 3 hydrogen molecules and 1 nitrogen molecule all colliding together at the exact same time to then form 2 NH3 molecules. That does not happen, okay? Right? So this chemical reaction that I have written here is, right, non-elementary step. It's not a reaction mechanism, right? But I can describe this chemical reaction through a reaction mechanism that has a bunch of elementary steps. Each one of those elementary steps is telling you what reactions are actually taking place. What molecules are colliding with other molecules to create new molecules, and so on and so forth. Okay? Right? Right? And so an intermediate, right, something that was being described, right, is right, an atom or molecule that is formed and then consumed during a reaction mechanism. Right? So as what was, right, being described, right, how you can have these elementary steps that make something and then that thing is later used, right? Those things are called intermediates, right? So intermediates will appear in your reaction mechanism, okay? And again, they're given the term intermediate because they exist intermittently. They exist for only short periods of time as they're being produced and then consumed quickly during the chemical reaction, okay? All right, actually, we already kind of talked about half-life, so I'll just get rid of that one. Okay. All right. So I have that reaction N2 or whatever. It's just an example of what is not a reaction mechanism, I guess. Right. Right. Just so we're clear on that. Right. That reaction is not a mechanism. That's just a chemical reaction, right? But for every chemical reaction, we can describe to it some type of reaction mechanism that's composed of elementary steps that show you how things are actually reacting to get you from the reactants to the products. Okay? During those elementary steps, other molecules and atoms right, might be formed, okay, and then later consumed, and those things are called intermediates, right? And they do not exist in your overall chemical reaction, right? So your overall chemical reaction just has reactants and products, right? But in the mechanism itself, there are these intermediates that for a given elementary step is a reactant or a product, okay, but do not appear in the overall chemical reaction. Questions about these definitions here? All right, so for example, right, I have this chemical reaction, NO2 plus CO going to NO plus CO2. right? The rate here is K times NO2 squared, right? That's the rate law. And I have this proposed mechanism, NO2 plus NO2 going to NO3 plus NO, and then NO3 plus CO going to NO2 plus CO2. Right, and so for this mechanism, right, what would be an intermediate here? NO3, right? NO3, 1 does not appear in my overall chemical reaction listed at the top, right? And NO3 is something that is produced in my mechanism and then consumed later, right? It's a product and then becomes a reactant in another step, okay, that occurs later, right? And if you add these two elementary steps, you'll get this overall chemical reaction, right? Now, why we care, right? So why we are talking about these reaction mechanisms at the same time we're talking about kinetics is because these things are very closely related with each other, okay? We use the ideas of chemical kinetics and the rates of reactions and their rate laws to be able to help experimentally determine what the reaction mechanism is. Now, I say the word determine, but we can never 100% know that whatever mechanism we propose for the reaction is what's happening, right? Because we can't just view these things at an atomic level, right, and see what things are actually reacting, right? But we can use a lot of things like measuring rate laws, okay, trying to measure intermediates that are formed, right, using spectroscopy and things like that to try to figure out, you know, and see if I can notice some small concentration of NO3 being formed while this reaction's going, right? There's different things we can do to validate a mechanism that we propose, right? But we can't know for 100% certainty that that is the actual mechanism, okay? And we can be pretty confident, right? And a lot of times we can feel very, very confident about these things, but, right? And again, so this idea of reaction mechanisms and understanding how chemical reactions occur is directly related with rate laws and rates of reactions. And so, right, so we'll talk about how we can get, right, the rate law from these elementary steps, okay? So, right, as a reminder, right, this is our mechanism. Each step is called an elementary step, an elementary reaction. Okay. All right. So, what would you say the molecularity is for this following elementary step? Is it unimolecular, bimolecular, or termolecular? Anyone take a guess as whether or not A, B, or C here? C. Okay, so a couple of C's, right? So yes, it is unimolecular, right? So the molecularity of an elementary step is just how many reactants do you have, okay? Right? So I have one reactant here, so it's unimolecular. If I had two reactants, it'd be bimolecular. Three reactants would be termolecular, right? So on and so forth, okay? Right? Now, termolecular reactions are a lot more rare, okay, to occur in an elementary step. And it's just because they're just a lot more rare to actually happen, right? For a termolecular elementary step, right, I need three things to collide at the same time in air, right? If I think about these things, say, occurring in gas phase, I got to have three separate molecules all reaching the same point in space at the same time. It can happen, but it's not going to happen very often, right? And so it's just a very slow reaction typically if you have a termomolecular elementary step, and is typically not and is just not common in most reaction mechanisms. For most reactions, your elementary steps are unimolecular or bimolecular. Okay. That doesn't mean that termomolecular steps don't exist, just they're not as common. Okay. Right? And so we talked about, right, how these mechanisms can be related with our rate laws, and how are they related? Okay. Well, the rate law for an elementary reaction can be directly related to its molecularity, right? Directly related to what is in my reactants, okay? So for the reaction listed here, I'm assuming this reaction is an elementary reaction, an elementary step, right? For that reaction, okay, it's saying NO2 and NO2 are coming together in space and colliding with each other, right? And so the rate at which that reaction occurs better depend on the concentration of NO2 and the other NO2, right? Because the more I have, the more collisions I'm going to have, so the faster my reaction should be, okay? And so because of this, right, because the elementary reactions are actually describing what is colliding, what are reacting with each other, right, the rate can be just written from the reaction itself. So the rate here is equal to the rate constant times concentration of this reactant times the concentration of this reactant, which is the same thing, right, NO2, NO2. So you just get NO2 squared, okay? Right? Now for a general chemical reaction, okay, so for example, right, in this chemical reaction here, right, the rate is not equal to the rate law is not equal to the rate constant times the concentration of the reactants, because this is a general chemical reaction, okay? But for these elementary steps, the rate law for each elementary step is equal to the rate constant times the concentration of the reactants, okay? So for this case, right, concentrations of the reactants is NO2 times NO2, okay? And so for elementary steps, I can get the rate law from the chemical reaction, but that's not true in general, okay? Right? When we were doing these method of initial rates and all these other examples, right, we were talking about general chemical reactions, right? And in those cases, the rate laws are completely independent of what the reaction looks like, right? What are they in the reactants, what are coefficients, things like that? Not dependent, okay? But for elementary steps, it is. Right? So again, just to sum up things, right, a reaction mechanism, right, is a series of elementary steps that sum up to give you the overall chemical reaction. And, right, for our reaction mechanism to kind of be valid, it needs to agree with an experimental rate law. Okay, so in lab, right, we would determine what the rate law is for our overall chemical reaction. And then we try to see if that agrees with our mechanism, okay? So to get the rate law from the mechanism, one thing that we typically do is we use the rate determining step approximation, okay? And what is what do you think the rate determining step approximation is saying or about? Yeah, right, so it's the slowest, right? So it's about, yeah, the slowest elementary step does what? Yeah. The rate of the overall reaction, right? So this is, right, the rate determining step approximation, right? That's saying, right, whatever the slowest step is in your chemical reaction, that step determines the overall rate of the reaction, right? It's like if we all wanted to try to run out of this door real quick because a fire started or whatever, right? To get outside, right, when you're in a room, it takes more time to have everyone get through the door than it does to have people to get just to the door, right? So people can get to the door quickly because there's more space for everyone to quickly rush to it, but then there's a limited amount of space to get through the door. So getting through that door is the rate determining step, right? It's the slowest step. How fast people can get out of the building is determined by how fast they can get through the door, not how fast can they get to the door, okay? So it's just that concept, right? That whatever is the slowest step is going to determine the overall rate for a reaction. Okay. So then our question here with this example we've been working with, NO2 plus CO going to NO plus CO2, right? The rate law is equal to K times NO2 squared. That's determined through experiment. And I have this proposed mechanism where I know the first step is slow and the second step is fast. And then the question is does this mechanism agree with our experimentally known rate law? Yes, it does, right? Let me write out here real quick. And I'll show what I got on the paper here. All right, so for these two reactions, just for the sake of it, I'm going to write out what the rate laws are. Yeah. Right, so for those two elementary steps, right, the rate laws were get these two things, right? Well, this was the slow step, so it's our rate determining step. So that means that the rate for this elementary step is the rate for overall chemical reaction, which agrees with the experimentally determined one. Okay. So the second step, the rate law here, KNO3 times CO, right? I think the reaction was NO3 plus CO forming NO2 plus CO2, I believe, right? And I guess the first reaction was NO2 plus NO2 going to NO3 plus NO, right? So that was our reaction mechanism, right? Our slow and our fast step, okay? Right? So let's say the second step was the slow step, right? Let's say NO3 plus CO going to NO2 plus CO2 is the slow step, right? And I have this rate law for my second step. What is wrong with using this rate law to describe the rate of my overall chemical reaction? Yeah. Oh, sorry. Let's pretend instead now it was the slow step, that this was slow and this was fast. Sorry. Yeah, right. So it's this guy here, this intermediate, right? The rate, right? I have K equals K times NO3 times CO, right? Sorry. Right. This NO3 times CO, right? Well, NO3 is an intermediate, right? And that is never going to appear in the rate law for overall chemical reaction, okay? Now, in this class, we'll never have to solve, figure out how to get rid of that intermediate to get an overall rate law, okay? But if you were to take certain upper level biochemistry classes or physical chemistry or things like that, you'll find ways and techniques to get rid of these intermediates from your overall rate law expression, okay? But just note that our rate law cannot include intermediates, okay? Because they're intermittent, right? We don't know what those concentrations are during the course of the chemical reaction. It's not something we can control, right, and easily measure and determine, but we can for reactants and products. So our rate laws need to depend on the concentrations of our reactants, right, and not, say, intermediates, okay? So this wouldn't be a valid rate for a chemical reaction because it includes an intermediate. Okay? So I'll just kind of make a note of that. But again, don't worry. You don't need to worry about ever solving for a rate law that has an intermediate existing in the final expression because they won't. Okay? We won't deal with that in this class. Okay?
If there is a question like that, and was asking, what's the rate law, and that one was just a reaction, would you say there's no rate law, or would you use the other one?
Basically, I mean, so you would just never be given something where an intermediate would appear as the rate law. I mean, or one of your possible answers, if there's a multiple choice, would be saying, need more information or something like that, and because it can't depend on an intermediate or blah blah blah, something like that. Yeah, but no, yeah, you'd be given examples like this where it has the slow step is the first step, because then it doesn't depend on intermediates, because an intermediate is never going to be in the very first step, because an intermediate first has to be produced in your reaction mechanism and then later consumed. So, yeah. So you'll just never run into a problem like that. Other questions? All right. So, right, given these are different elementary steps, okay, or assumed to be elementary steps, right? So these are different reactions that are assumed to occur in a single step, right? And so the question is given that these are the rate laws for these given reactions, right? Right, which one of these four reactions actually does occur in a single step, right? While the other three will not. Okay. Right, and so kind of this question is asking, right, assuming those reactions take place in a single step, do the rate laws for those reactions agree with the experimentally determined rate laws on the right? All right. So let's write out, right? If we assume these four chemical reactions are all single step reactions, right? So these are effectively elementary steps, right? They just occur in one single step, right? What is the rate law going to equal for each one of these guys? So the first one was the rate going to equal? It's okay. NO2 squared, right, times F2. Okay. For the second reaction, the rate is going to equal what? Oh, sorry. Okay, and then H2 times Br2. Okay. This next one, right, NO, O2, and then this final one, I'm messing up on that. CO. Okay. NO2, that's a CO. Sorry. Right. Right. And so if you compare these to the ones on the slides that we'll flip back to, right, see that only this one does the rate law, right, assuming this is an elementary step, right, its rate law is the only one that agrees with the experimentally determined rate laws, right, that are given on the slide, right? So if you go back, right, this one, it has to be NO2 squared, not just NO2, right? This one needs to be Br2 to the 1, not Br2 to the 1/2. And this needs to be NO times CO, not NO2 squared, right? So C here is the only one, right, where the rate law of that reaction, assuming it's an elementary reaction, agrees with the experimentally determined rate law. Okay. Questions about this example? All right. So related with these reaction mechanisms, right, we're talking about these elementary steps which talk about how things are colliding and reacting with each other, okay, right, on a molecular level, okay. And related to that is this concept of collision theory. Okay, and so what is collision theory? What is that stating? Related, so it's for a reaction to occur, certain things have to happen, right? Right, molecules need to actually one collide, right, two with the proper orientation. So they need to collide with the proper orientation, and three, enough energy to react. Right? So that's basically just what collision theory is stating, right? Their molecules need to collide with the proper orientation and enough energy to react. Okay? Right? And so, right, given this idea of collision theory, right, how does increasing the temperature then affect the rate of a reaction? Right. Like so let me phrase this. Out of the things that need to occur, right, according to collision theory, like 1, 2, and 3, right, what of those things will be impacted by temperature? Yeah, right. So the energy, right, is increased with increasing temperature, right? And what is, and the effect of that, right, is that one, right, the molecules will then collide more often, right? Because if you have things moving faster, they will hit each other more frequently, right? Makes sense, right? So they'll collide more often, and each collision will be more more likely produce products, I guess is how I'll phrase that, right? Right, because we said, right, you need enough energy to react, right? Two molecules can collide in collision theory, right? So collision theory, right, again, is stating molecules have to come together, they got to collide in the right way, and they have to have enough energy to react, right? And so if I increase my temperature, things are colliding more often, so it's more likely they're going to collide in the correct way. And when they collide, because they have more energy, that means those molecules, right, will more often have enough energy for the reaction to occur. Okay. Right, I'm going to actually, I'm going to make a new slide in a second, right? So I actually want to ask the question. Is the energy barrier called? Yeah, for a called. Was that energy barrier called for a reaction to occur? Right. It's called the activation energy. Right. The energy barrier. Right. That's determining whether or not a reaction will occur or not is that activation energy. Right. The amount of energy required to get to the products. Okay. Right. And as you get towards the products, right, as your reactants go from reactants to products, right, when they're at this activation barrier, the geometry that they occupy is considered or called the transition state, right? You're transitioning at that point from reactants to products. Okay. And again, a lot more of this is discussed in more detail in the lecture slides and the videos that are posted online. Okay. Actually change this around just so that there's more things, right? And so, right, and so that is the idea behind collision theory, right? Is just discussing how molecules are colliding, why every collision is not a successful collision, and why temperature then affects the rates of chemical reactions. Okay? So questions about collision theory, temperature dependence, how it works. All right. So given the kind of this idea of catalyst, or sorry, of collision theory, right, and these reaction mechanisms and such, okay, what, oh, let's actually, sorry, we'll actually just first, I forgot I had this slide here, right? So the temperature dependence of the rate comes in through the rate constant K here, right, which is given by this equation called the Arrhenius equation. Don't need to memorize it whatsoever. I'm just showing you here that there's this kind of the natural log of your rate constant K is proportional to 1 over the temperature K. So if you plot the natural log of K versus 1 over the temperature, you'll get a straight line with a slope that's related with the activation energy. Okay. And so, right, this equation is just here to kind of show you again how K and temperature are related, and the fact that in the lab, often how people measure these activation energies, right, that this barrier for a reaction to occur is they measure the rate constant as a function of temperature, okay? And when they do that, they can then plot the natural log of the rate constant on the y-axis, 1 over temperature on the x-axis, and then from the slope of that line, they will be able to back out what the activation energy is. Okay, so this is a very common technique used in the lab to determine activation barriers for given chemical reactions. Okay. So there's a question here for collision theory. We just need to know why it happens, etc. for the exam. Yeah, I mean, there's no real kind of numerical problems with collision theory per se. I mean, I guess this Arrhenius equation is related with collision theory, but there's not going to be any numerical problems on here. Any questions on the exam on collision theory are all conceptual. Okay. So yeah. All right. Okay. So now, right, catalyst. So what does a catalyst do for a chemical reaction? Yep, exactly. So catalyst, right, creates a lower energy pathway or reaction or pathway. Another way of saying pathway, I'll say action mechanism, right? Right. It's creating a new reaction mechanism, a new way this reaction can occur. That's at lower energy. Let me see. A new pathway reaction mechanism. A lower energy activation barrier. Turn speeds up the reaction. Right? Right, catalysts, right? We know catalysts, right, speed up a chemical reaction. Okay. The idea they catalyze a reaction, they speed it up. Okay. And how they do it, right, is by providing an alternate pathway. Okay. Right. For the reaction to occur, that alternate pathway will have a lower activation barrier. Okay. And that's how it speeds up the reaction. Okay. Catalysts themselves, right? In a chemical reaction, a catalyst is a pure catalyst is not consumed in that reaction, right? So for an overall chemical reaction, the catalyst only speeds up the reaction. It itself is not used, right? So you should technically be able to use a very small amount of a catalyst to cause a very large amount of a reaction to occur, because the catalyst itself is not consumed. Now, not all catalysts are that efficient and that robust to be able to cause so many chemical reactions. It's related with the idea of how much you can use a catalyst is related with its like turnover rate. How many reactions can a catalyst cause before it accidentally breaks down, right? Decomposes or something like that. Okay, right? And catalysts are used all the time in both industry, right, as well as within our bodies, right? Proteins in your bodies, a lot of them are just catalysts. Right? They just catalyze certain chemical reactions, right? They're called enzymes, right? Right, you think your cars use catalysts in their catalytic converter, convert certain gas molecules to less harmful molecules, okay? Right? But these things, right, are not consumed as the reactions take place, okay? Especially if they're efficient. Right? So in a reaction mechanism, how would you tell the difference between a catalyst and an intermediate? Yeah. Yep, exactly. Right. So both intermediates and catalysts do not appear in the overall chemical reaction, right? But a catalyst is consumed, it's used up at the start of your reaction, but then produced later. Okay. And an intermediate is produced during your reaction, but consumed later, right? So a catalyst appears as a reactant, then a product, while an intermediate appears as a product, then a reactant. Okay, right? Right. Intermediates exist only intermittently during the chemical reaction, right? A catalyst is something that you can measure and have some amount of before the reaction takes place, right? Okay. And so in this example here, right, the overall, right, so freons, right, that were used in a lot of aerosol sprays and such, right, introduced chlorine atoms into the atmosphere. Those chlorine atoms catalyze the reaction of ozone, right, which is O3, okay, ozone O3, with oxygen atoms to form O2. Given this mechanism, okay, so in this mechanism, what is going to be a catalyst and what is going to be an intermediate? Yep. So, right, so you look at these two elementary steps added together, right? You will get the overall chemical reaction if you add these two reactions together and cancel out common things on the reactants and product sides and simplify, right? And we see here that Cl gas is consumed in our mechanism and then produced later on. So that is a catalyst, okay? It doesn't appear in the overall chemical reaction, but it's a reactant and then a product, while ClO, right, is produced and then later consumed. So that is a product and then a reactant. So that's an intermediate. Okay. The CO is our catalyst and ClO is our intermediate. Question? Oh, right, we just did that. Okay, well, we can look at all these things, right? So we just kind of talked about some of these, right? But so which of these statements are true? O2 a reactant, ClO an intermediate, O3 is decomposed to O2 and O in the overall reaction, Cl is a catalyst. Okay. Right, so we just talked about how Cl is a catalyst. We also talked about ClO is an intermediate, okay? And then in the overall chemical reaction, O3 is not decomposing to form O2 and O, right? O3, right? If you add these two reactions together, you'll get O3 plus O forms 2O2, okay? So O3 is not decomposing, it's reacting with oxygen to form O2. And then O2 itself is a product, not a reactant, okay? Because again, if you add those two reactions together, you'll get this overall chemical reaction. Right, so only 2 and 4 here are true. Okay. Other questions? All right, so given this overall chemical reaction and these two steps in our mechanisms, right, what are going to be intermediates and what are going to be catalysts? Okay. There's the question here real quick, so I'll go back real quick to this question. So why is ClO not an intermediate? ClO is an intermediate. So I was saying 2 and 4 are correct. That ClO is an intermediate, that is true, and Cl is a catalyst, that is true. It's 1 and 3, O2 is a reactant, and O3 decomposes to O2 and O. Those are false statements. Okay. Yeah. No problem, no problem. Just want to make sure it's clear. So you are correct, ClO is an intermediate. All right, so then back to this example, right? So what here is a catalyst, and what here are intermediate. All right, so there's some suggestions on here in terms of what are catalysts and intermediates. So let's go through these one at a time. So Br minus, is that going to be a catalyst, an intermediate, reactant, product? What is that? It's going to be a catalyst, right? Br minus does not appear in our overall chemical reaction, so it's definitely not a reactant or product. So it's either got to be a catalyst or an intermediate. In this case, it's consumed in step 1 and then produced in step 2, so it is a catalyst. H2O2, just our reactant, right? H2 or H plus, sorry, is also a catalyst, right? Because H2 plus is a reactant, and then later it comes back out as a product, right? So H2 plus is also a catalyst for this chemical reaction, okay? And then Br2, an intermediate, right? It's does not appear in the overall chemical reaction, and it is produced and then later consumed. That is an intermediate. H2O is a product, right? And then we talked about all these guys, and O2 here, last guy here is a product, right? So you have two catalysts in this reaction, Br minus and H2 plus, one intermediate, Br2, and then our reactants and products, right, that are given in the overall chemical reaction. Questions about identifying those species of this mechanism? All right, so that is the end of chapter 14, okay? And that's it for things that are covered on the exam. I'm not gonna bother trying to like squeeze in a few minutes of chapter 20 or anything like that. So we'll end here. I'm happy to answer any questions people have. But otherwise, you're also free to leave. Are there extra of the participation questions floating around somewhere? If not, and someone didn't get any, please come on up and come talk to me real quick. Oh yeah, thank you, Dylan, for reminding, right? There's a quiz on chapter 14 that's due by tomorrow, okay? It'll open up this evening. It'll be due by tomorrow evening at 7 p.m. Right? So I tried to have it open up today after people should hopefully be done with classes. And then I give them 24-hour windows, so it will be due by Tuesday at 7 p.m. Okay?
So I had a question for an intermediate. I understood catalyst because you explained it well. You said it's consumed and then it's produced.
Yeah.
Catalyst. But I'm not too sure on the intermediate.
Intermediate, if it's produced and then consumed. So it's the exact opposite of the catalyst. Produced and then consumed.
So it would be T.
Yep.
Cool. Okay. That makes it so much more clear.
Yep. Okay. Yeah, just write down your name and A number here. Thought I printed out plenty, but I don't because I didn't hand them out. I think some have somewhere. Actual ones got taken.
And then if last week I missed it as well, like you said you were gonna email me, and then I didn't get an email. So
Well, no, you wrote down the
Yeah,
stuff, right?
I wrote-
Yeah. So no, that was it. That's all you need to do.
Oh, okay.
Yeah.
So last week
I had sent you an email. I wasn't able to come to class Sunday, not by choice, like I had to. But I didn't do the participation. I didn't have like anything pop up. I actually totally forgot to email you about that.
Okay.
But I did attend both Zoom meetings for like Monday and Wednesday.
Yeah. Yeah. So I just don't worry about it. Like I dropped like a number. Like I dropped a couple of weeks of participation from the semester.
Oh, okay.
Just for things like that where people have to miss a day for whatever, right? I mean, that's the same type of thing with like during normal times or whatever, right? All this extra restrictions and things like that. You know, I do the same thing where I just, you know, people can miss a number of days of class and it's not going to affect their grades. Yeah, so don't worry about it.
Okay, thank you.
Yeah, no problem. Yeah.
So I understand we weren't doing it in this class, but to find the reaction of the, if you have a three-step mechanism, like fast, slow, fast, would you take the reactants of the slow step and put them over the products and the react, or like?
Well, so there's two main ways you can try to get it.
So I know you have to use the previous steps if you like have the slow step after, I think, right?
Yeah, so it depends on if you're, so there are two types of kind of approximations that you can use. One's called the steady state approximation, and another one's called the pre-equilibrium approximation. So if you have a slow step that's preceded by a fast equilibrium step, then you can use essentially the equilibrium constant and products over reactants and things like that to get out intermediates and stuff like that. You know, so yeah, so those things involve stuff that, you know, either we haven't talked about yet, or the steady state approximation is yeah, it just involves math and other things that are what we're doing. So, yeah. All right, you're welcome. So the question here, I want to clarify, exam 1 is this Wednesday, we're in class, and next Monday on Zoom. No, so, right, so if you attend class, right, so there's 3 groups in this class. There's group A, group B, and group C. Group A attends on Mondays. They will take their exam a week from today. Group B attends on Wednesdays in person. They will take their exam on Wednesday this week. And then group C are people that are online. They will take their exam either Wednesday or Monday, and they've been broken apart into 2 groups. Okay. So if you're online only, check out what group you're in. I know there's at least one person that somehow got missed from there, so I'll update that today. But yeah, if you're online only, check what group you're in to see whether or not you take the exam on Wednesday or Monday next week. And if you normally attend class face-to-face on Wednesday, then this Wednesday you'll take the exam. If you normally attend class face-to-face on Mondays, then a week from today you'll take the exam. Okay. Hopefully that kind of clarifies that.
Yeah, so I emailed you the other day about having to switch to online temporarily just because I had a roommate situation.
Yeah.
But I emailed you and said that everything was all good to go, except for negative.
Okay.
So I was just wondering if like I could get switched back.
Yeah, no, that's what, I mean, all I literally do is like on Canvas, I just add you to like this online only section.
Yeah.
I don't like remove you from anything. So I'll just like remove you from that just so like extra assignments,
Yeah,
things like that don't
because
pop
I
up.
noticed like all this like missing. I was like, what?
Yeah, no, I'll do that. When did you email me saying that you were fine?
It was sometime last week. I honestly
Okay,
don't
yeah.
remember.
If you can just send me another email to
Okay.
remind me, because if I apparently haven't done it yet, then I probably forgot to do it, and I apologize about that.
Yeah, no, it's all
So
good.
yeah, just send me another email, and I will remove you from the online only.
Okay.
group.
All right. Thank you.
Yep.
Have a good day.
All right. So did I get to your question about when to take the exam? Did you hear that? I don't know if you're still here. Right? Yeah. Okay, I just want to make sure. So hopefully that kind of clarified that for you. Yeah, if there are no other questions, then I'll close this up. But if someone has any last question, feel free to ask. All right, so looks like there isn't anything else. So I will close down this meeting and see some of you Wednesday who are taking the class in person or who are taking the exam online.